Welcome to the Deep Dive. We're here to unpack the latest research, making complex topics clear, quick, and useful for you. Today we're digging into something fascinating. The real power, but also, maybe, the hidden limits of these incredibly powerful new language models. You've probably seen the headlines models like OpenAI o1, DeepSeek R1, Kimi 1.5. They're doing amazing things, especially with complex logic, like high-level math and coding.
Absolutely. And a key technology behind these leaps is something called reinforcement learning with verifiable rewards, or RLVR. The idea is, well, it's pretty neat. The model generates something, say, a solution to a math problem, and gets a simple automatic thumbs up or thumbs down. You know, a reward of 1 if the final answer is right, or if the code passes its tests, 0 otherwise.
Right, so it's scalable. You don't need a human grading every single step, which is expensive and slow.
Exactly. And historically, we've seen RL do incredible things, like in Go or chess, where algorithms discovered totally new superhuman strategies all on their own. So the common thinking, the sort of prevailing wisdom, has been that RLVR would do the same for LLMs, that it would let them self-improve, learn new ways of reasoning, really push beyond what the original base model could do.
Okay, let's unpack that.
Yeah.
Because the research we're diving into today suggests this picture.
Right.
Well, it might be missing a really crucial piece. We're asking, does this RLVR approach actually expand the fundamental reasoning ability of these models? Or is it maybe just making them better or more efficient at using the abilities they already had?
And to figure that out, our mission here is to look past just the average performance. We need a way to measure the model's true reasoning boundary, its maximum capability, and then see if RLVR actually pushes that boundary out.
Yeah, so the first hurdle researchers hit was that the usual ways of measuring performance weren't really cutting it. If you just look at, like, the model's first guess greedy decoding, or what's called pass-at-one accuracy, meaning it has to get it right on the very first try.
Exactly. That only tells you about its sort of average behavior, its most likely path. It doesn't show you the full extent of what it could do on harder problems.
Right, because for something really complex, maybe the first answer is wrong, but if you let it try a few times, maybe try generating different lines of thought, it might eventually land on the correct one. So pass it one underestimates that.
Precisely. It misses the latent potential. So to capture that, the researchers relied heavily on a much more robust metric, pass at K.
Okay, pass at K. So for you listening, the idea is, instead of just one try, we let the model generate, say, different outputs, different potential solutions, and if any one of those dollar attempts is correct, even if it's the 10th or the 100th try.
And then we count the problem as solved by the model.
Yes. So the pass at K score tells you the proportion of problems the model could potentially solve if you give it a lot of shots. It maps out its maximum capacity, its true reasoning boundary, much more effectively.
Okay, so the hypothesis then is simple. If RLVR is genuinely boosting reasoning power, then the RL-tuned model should solve more unique problems overall. It should have a significantly higher pass at K score than the base model it started from, especially when dollars is large, like, say, 100 or 1,000.
Okay, but here's where things get really interesting and honestly quite counterintuitive. The data showed, well, pretty much the opposite, didn't it? And this wasn't just a one-off. It held up across different models, different tasks, math, coding, even visual reasoning.
Yeah, it was remarkably consistent. We saw this clear split. For small values of dollars, like K$1, the RL-trained models were definitely better, no question. They consistently outperformed the original base models.
Okay, so RLVR does work in that sense. It makes the model more efficient, right? More likely to nail the answer on the first attempt.
Absolutely. It boosts sampling efficiency dramatically, makes the model much more reliable for that first shot answer.
And you might think, well, isn't that what we want? A fast, reliable answer. Why do we care about performance way out at, like, K102T for $4?
We care because that high ADAL value tells us about the model's ability to solve the really hard, unique problems, its ultimate reach. And that's precisely where the base models, the ones without the RL tuning, consistently caught up. And actually, they eventually surpassed the RL-trained models.
Surpassed them. So the original model, given enough attempts, could solve more unique problems than the tuned one.
That's exactly what the data showed, across the board. It means the overall scope of reasoning, the total set of problems the RL model could potentially solve, had actually shrunk.
Huh. There's an analogy in the research, like a search tree. RLVR is like highlighting the common correct paths, making them easier to find. That's the efficiency gain. But is it possible that in doing so, it's sort of pruning away or making it harder to find those less common, maybe more complex paths that the base model could have found, even as rarely?
That seems to be exactly what's happening. RLVR biases the model towards the known good stuff, the paths that get rewards. But that focus, that optimization, comes at the cost of reduced reasoning scope. The key insight quantitatively was watching this over training. As RLVR training progressed, the average performance, pass at 1, went up great, but the total coverage, measured by something like pass at 256, actually started to decrease.
Wow, so it's a trade-off. You gain immediate reliability, but you might lose some of that deeper, harder-to-reach potential.
Yeah.
Okay, so what's the deep reason here? For those of us hoping LLMs would just keep learning new kinds of smarts on their own, this seems important. Why isn't RLVR expanding that fundamental capacity?
Well, the analysis really drilled down on this. And the core finding seems to be that the RLVR process, as it currently works, is fundamentally bounded by the knowledge already present in the base model. It doesn't seem to be enabling the models to solve genuinely new types of problems they couldn't solve before. It's just making them much better, much more efficient at finding the solutions for problems that were already somehow within the base model's latent capabilities.
The potential was already there, just hidden.
Exactly. The set of solvable problems doesn't really expand. It's more about improving access to the existing solutions.
And the evidence for this was pretty stark, right? Especially looking at which specific problems each model could solve on those tough math benchmarks like AIN or Math 500.
Oh, absolutely. They looked at the overlap. Cases where the base model could solve a problem, maybe needing lots of samples, high dollars, but the RLVR model failed completely.
Yeah,
That was surprisingly common, something like 13% on the AIM benchmark.
13%. Okay, but what about the other way around? Cases where the RLVR model solved something the base model absolutely could not. That would be the evidence for new capacity, right?
And that was incredibly rare, like close to zero, between 0.0% and maybe 1.0% across the different hard data sets.
Wow. Okay, so that really does sound like
Right.
the RL model solvable set is almost entirely just a subset of the base model solvable set.
Precisely. That's the smoking gun. RLVR seems to be specializing the model, honing its efficiency on known territory, rather than expanding the map.
It's like taking a big general toolkit and just making the Phillips head screwdriver super easy to grab, maybe even welding it to your hand.
Yeah, it's not a bad analogy.
But you might lose the ability to easily find that weird Allen key you need for one specific job later.
Right. And we can actually see this technically using something called perplexity analysis. Perplexity basically measures how surprising a sequence of text is to a model. What they found was that the correct reasoning steps, the successful solutions generated by the RLVR model, had very low perplexity when judged by the original base model.
Low perplexity, meaning the base model wasn't surprised by them at all. It already thought those reasoning paths were plausible, maybe even likely.
Exactly. It confirms the RLVR isn't inventing fundamentally new ways of thinking. It's just learning to strongly prefer the good reasoning paths that the base model already recognized as high quality. It's sharpening the distribution within the base model's existing knowledge, not pushing beyond it.
Okay, so if RLVR isn't the key to expanding raw reasoning power, just optimizing access, does anything actually expand that capacity? You mentioned distillation earlier.
Right, distillation. It's a really different approach. RVR, as we've seen, is about optimizing the model's own outputs based on a simple success-fail score. Distillation is more like teaching. You take a much larger, more powerful teacher model, have it generate detailed, step-by-step reasoning for problems, and then you train a smaller student model to mimic those specific reasoning patterns.
Ah, so it's explicitly transferring knowledge and strategies from the better model, not just rewarding the final answer.
Exactly. It's designed to impart new patterns, new ways of thinking that the student model might not discover on its own. It's knowledge transfer, fundamentally.
And did the results bear that out? When they looked at distilled models, like I think DeepSeek R1 Distill was an example.
Yes, and the difference was striking. The pass at K-curve for the distilled model wasn't just better at low dollars. It was consistently and significantly higher than the base model's curve, all the way out to large K-dollar values.
It solved more unique problems overall.
Correct. Showed a genuine expansion of the reasoning scope, the reasoning boundary.
Okay, so that's a crucial distinction then. Distillation seems to add new capacity, while current RLVR primarily optimizes access to the capacity that's already there. And it's really telling that this wasn't just about one specific RL algorithm being flawed, right? They tested several different ones.
Yeah, they ran experiments with, I think, 6 popular policy gradient algorithms, PPO, GRPO, Reinforce, plus, and others. And the pattern was the same. They all improved past at 1, that initial efficiency, but they all hit that same ceiling when it came to pass at K, the maximum capacity. None of them significantly outperformed the base model at high dollars.
Which points to something more fundamental about the setup.
It does, and they quantified this limitation with something called the sampling efficiency gap, basically, how far the RL model is from perfectly utilizing all the potential solutions hidden within the base model. And that gap remained really large, consistently over 40 points across the different algorithms. Even just accessing the existing potential is still a huge challenge for current RL, let alone expanding beyond it.
So let's get to the why. Why is RL seemingly so constrained here when we know it can be incredibly creative in other domains, like games?
The researchers point to a couple of key things. First, unlike traditional RL that often starts from a blank slate in a game, RLVR starts with this incredibly powerful, complex, pre-trained language model. That's a huge head start, a strong prior.
But the action space, the sheer number of possible things the model could say or write, it's astronomical compared to a Go board, right?
Infinitely larger, practically. It's combinatorial.
Yeah.
And here's the kicker. If the model tried to explore outside the patterns it learned during pre-training,
Yeah.
the vast majority of those explorations are just going to be gibberish, nonsense, things that will immediately get a 0 reward from the verifier.
So any attempt at true novelty, at stepping off the known path, is almost guaranteed to be punished immediately.
Exactly. The environment provides brutal negative feedback for straying too far. So the optimization algorithm, the policy gradient, quickly learns the safest strategy. Stick to what you know. Maximize the probability of generating responses that are already likely under the strong pre-trained prior and have some chance of being correct. Don't wander into the vast wasteland of nonsense.
So it becomes self-limiting. It's forced to just refine the known good stuff, constraining itself within the base model's boundaries.
That seems to be the core mechanism, which really points towards needing new approaches if we want RL to break out of this.
What kind of approaches? What are the future directions?
Well, the limitations might stem from this lack of effective exploration, or maybe the very simple single-turn interaction with the verifier just getting one final score. People are thinking about, well, obviously continuing to scale out training, but more fundamentally, moving towards maybe a multi-turn RL agent paradigm.
Multi-turn, like the model interacts more with an environment.
Yeah, richer, ongoing interactions, maybe with the simulation or tools, or even back and forth with the verifier, allowing the model to try things, get feedback, refine its approach over multiple steps, generate experiences to learn from, not just optimize static outputs. Some are calling it the era of experience for these models.
That makes sense. Moving from just being an optimizer to being more like an actual learner interacting with a world. Hashtag outro. Okay, let's try and wrap this up with the main takeaway for you. What we've learned today is that while RLVR makes models like OpenAI 1 incredibly efficient, making them much better at quickly finding answers they could already find, their ultimate capacity to solve unique, challenging problems seems currently limited by the base model they started with. Right now, its strength is efficient sampling, reliability on known ground, not necessarily discovering fundamentally new reasoning abilities.
That's right. So if your goal is to get a model to solve types of problems it genuinely can't tackle today, this research suggests distillation learning directly from a stronger teacher might be a more promising path for expanding that core capacity, at least with current methods.
Good summary.
But here's a final thought to leave you with, something that really struck me from the source material. The analysis showed examples where the base models, before any RL tuning, actually contained these incredibly long, complex, almost reflective chains of thought that led to correct answers on hard problems. They just very rarely sampled them. They were hidden gems.
Wow. So the deep reasoning is potentially there, just buried?
It seems so, latent within the base model. So the provocative question is, given that capability is hiding in there, what kind of reward signal, something maybe richer or more nuanced than just a simple 0 or 1 on the final answer, might we need? What kind of guidance could unlock that latent complexity efficiently without inadvertently forcing the model to narrow its focus and lose that precious reasoning breadth?
That's a great question to ponder. How do we guide discovery without stifling it? Fascinating stuff.